Okay, so we have been talking about power representing functions as power series, and we've done some examples, a couple of examples, three actually. And the last example, we actually differentiated a power series in order to find, well, it was involved to help us find a power series for a particular function. We can also find a power series for a function by integrating as well, by integration. So like one of the questions here in exam, this is now in your ebook, section 8.6. Find a power series representation for the natural log of 1 plus x and its radius of convergence. And what they do, I'll show you here. How do they get that? How do they get that? Well, here's what they do. They recognize that the log of 1 plus x is equal to the antiderivative of 1 divided by 1 plus x. I mean, right? Now, of course, you have a constant of integration, but let's not worry about that. The integral of 1 divided by 1 plus x is the natural log of 1 plus x. If you differentiate the natural log of 1 plus x, you'll get 1 over 1 plus x. Well, 1 over 1 plus x, okay, can be written as a power series. Okay, it can be written as the power series that they show above. 1 over 1 plus x is that power series that you see above. 1 minus x plus x squared minus x cubed and so forth. So the natural log of 1 plus x is the integral of 1 over 1 plus x, and that's the integral of that power series. Well, the integral of a sum is the sum of the integrals, so we can integrate term by term that power series, and then that gives us a new power series for the natural log of 1 plus x. Okay, so the natural log of 1 plus x equals that power series that you see there. Okay, and you can make use of that information, okay, for your homework. In other words, you don't have to derive the power series for the natural log of 1 plus x. You have it there. So if I go down a little bit, there's a formula for power series for the natural log of 1 plus x. It turns out that the constant of integration will equal 0. If you put x equals 0 in when they derive what's above there, if you put x equals 0 in there, you know the power series has to be true for the values of x over interval of convergence. So the constant of integration, by putting x equals 0 in to the power series, you determine that the constant of integration equals 0. And so there's your power series for the natural log of 1 plus x. We can also have a power series for the arctangent of x. Okay, so they do in example 7, they show how to find a power series for the arctangent of x, and there it is. And in your homework, they have for section 8.6, I believe it's the second or third example, they take you through how to get that power series. So now we have power series for multiple, for the log of 1 plus x and the arctangent of x. And given that, we ought to be able to do a problem involving an integral. So let me bring up another example here. Okay, let's do this example here, okay? Let me give you a moment to copy it down. Okay, so this is certainly an interesting problem. Is there an do you know offhand of can we find the antiderivative of x minus the arctangent of x divided by x cubed? Do you know offhand if we can get an antiderivative on that? Is that easy to do? Can you use any of your integration techniques? Integration by parts, use substitution, partial fractions, is that gonna? So what I'm asking is, if you had, let me clarify what I mean here. If you had a problem where it says find the integral of x squared dx, you wouldn't need a power series, right? You would just say, okay, that's x cubed over 3 plus a constant, because you know the antiderivative of x squared is x cubed over 3. But here we have the integral of x minus the arctangent of x all divided by x cubed. Do we know the antiderivative of that? Is that easy to do, to get the antiderivative? No. Daniel says no, and I agree. All right, so what are we going to do? Are we just, let's say we had an application that required us to find, to compute this indefinite integral. Well, what if we can't get the antiderivative, what if we could express this indefinite integral as a power series? If we could do that, then we could do the problem, and that's what we're going to do. So let's begin here. We know there's an arctangent involved, and it can be shown that the arctangent of x is this power series, where the interval of convergence, of course, is from -1 to 1. So we can just use that fact. Okay, we can use that fact. Okay, so what would we do? What would we do with this? Now, what you notice I do, and this is helpful, I write out some terms. I write out some terms of this power series. And what I'm going to do, I write out the first four terms. For this integral, I'm going to replace the arctangent of x with its power series. And in this case, writing out the terms of the power series like I do here is helpful. Why is it helpful? How does writing out the terms of the power series, like I've done here, help us simplify the numerator? Let me just so you understand what I'm doing here is I'm replacing the arctangent with its power series. And that power series is given in example, it comes from example 7 in the textbook, section 8.6. But what I'm going to do is put in, rather than put the summation in for the arctangent of x, the summation formula, I'm going to write the summation formula as like this. And I'm saying that's helpful in this problem. Why is it helpful? What nice thing happens here when I do that? Does anything cancel out? Do any terms cancel out? In the numerator there? That's right, Yonatan, the x terms cancel out. This x term here cancels out with this x term here, and the minus distributes across all the terms, giving me then in the numerator the power series x cubed over 3 minus x to the 5th over 5 plus x to the 7th over 7th minus and so forth. Now what we're going to do is we're going to take every term in the numerator and divide that term by the x cubed in the denominator. And that's going to give me the integral of 1/3 minus x squared over 5 plus x to the 4th over 7th and so forth. Please let me know if you have any questions at all. So like you know, maybe I'll just, you know, how do I get this 1/3 here? How do I get that 1/3? Well, if I take x cubed over 3 and divide it by x cubed, okay, that's like x cubed over 1. That's x cubed over 3 times 1 over x cubed, and that gets me 1/3. See? That's how I get the 1/3. And you can, and if I take x to the 5th over 5 and divide it by x cubed, you know, I'll get x squared over 5. Okay, because if you have x to the 5th over 5 and you multiply it by 1 over x cubed, that's the same as dividing by x cubed. That gets you x squared over 5. So is this helping, this little additional stuff I'm kind of doing here? Does this help? For how many of you is that helpful? Or who finds that helpful? Okay, good, Daniel. Good. All right. Thank you. All right. Just like I would do in a face-to-face class. I teach a face-to-face class on the Germantown campus. It's a Calculus 1 class. And I do this exact same stuff with them. So I'm doing it with you. So, all right, we have the integral now of this series. Now what I'm going to do is I'm going to go ahead and I'm going to go to the next page. That's all right. All right, I'm gonna go ahead now and write the series for. I'm gonna write the summation formula for this power series here. Turns out the summation formula that's going to work has a -1 to the nth power, an x to the 2nth power, divided by 2n plus 3. Now maybe I'll just go to let me just go to the whiteboard real quick and maybe help you with that a little bit. Okay, so right, hold on. So, you have a third minus x squared, sorry, over 5 plus x to the 4th over 7. I have the first 3 terms. And of course, this first term is when n is 1. Second term is when, well, I want to be careful here. If I want my power series to start at n equals 0, that's fine. So first term starts at n equals 0, second term at n equals 1, third term at n equals 2. Okay, so the first term, I know because the series alternates, it's an alternating series, I'm going to need a -1 to some power. Well, the first term's positive, so -1 to the nth power would work because -1 to the 0th power is 1. Okay, and so I know, I know, well, let me just do this here. Let me just do this. One-third equals what you see there. Hold on, class. Trying to show a little detail here. Okay, so what I'm trying to just remember, like the sequences, how you wrote out some terms enough so you can figure out the pattern. Well, that's what I'm doing here. I'm looking at the first 3 terms where n equals 0, n equals 1 is n equals 2, and I'm trying to come up with the the formula here. And I think we have the pattern. The pattern is the pattern based on the first three terms, okay, is going to be -1 to the nth power times x to the 2 to the nth power all over 2n plus 3. That's the pattern. That's the pattern that I'm seeing based on writing out the first three terms of the series, where n equals 0, 1, and 2. Is this okay? Are there any questions on this? The reason I need to write it was useful to write the power series. It was useful when I substituted in the power series for the arctangent of x to write out the terms of the power series so I could simplify my expression inside the integral. But now that I've simplified the expression inside the integral, I want to go back to finding a power series for finding a formula for the power series inside my integral. And that's what I've done. You need to have x to the 2nth power because you have even powers here. Even x is to even powers. You know, x to the 0th power is 1, x squared, x fourth, x to the 6th, and so forth. Okay, that looks good. Any questions on that before I go back to the problem here, solution? All right, just trying to fill in some details. Okay, hold on here. Okay, so this is then where we're at. We're here. And now we have the integral of a sum. The integral of a sum, hey, an integral of a sum is the sum of the integrals. If you have the integral of f plus g, that equals the integral of f plus the integral of g, right? So the integral of the sum is the sum of the integrals, right? And now what you have to do is you have to integrate you have to find the integral of -1 to the nth power x times x to the 2nth power divided by 2n plus 3. But the integral is with respect to x. So the -1 to the nth power over 2n plus 3, that can be brought out in front of the integral. Indeed, it can, because the integral is with respect to x. And the antiderivative of x to the 2nth power is x to the 2n plus first power over 2n plus 1. So now we have an expression for our integral. In other words, so the integral of x minus the arctangent of x divided by x cubed dx, that is going to equal this beautiful power series. And again, the interval of convergence is, I mean, we use the formula for the arctangent, okay? We use that formula. So hold on here, one moment. One moment, everybody. The interval of convergence is x is between -1 and 1. Yes, Yonatan, question?
Since we're doing the sum times an integral, wouldn't we have parentheses around x to the 2n plus 1?
It's the sum of a bunch of integrals.
Yes, but we're also multiplying it. We have
No, you're not multiplying.
We're not
You're
multiplying.
Not multiplying. No, no. Good question. Good question. Here you have the integral of a sum. Let me use the blue here. Here you have the integral of a sum. The integral of a sum is a sum of the integrals. See that?
Yes. My question is on the fourth and fifth row.
Fourth and fifth row. Oh, okay. Hang on. Okay.
Is that
so
not?
Yes, you are multiplying here. You are multiplying the integral of x to the 2nth power. You are multiplying it by that, yes.
Then wouldn't we have parentheses around the x to the 2n plus 1 over 2n plus 1 plus
I could put them there, and indeed I could if I want. I mean, I have a times here, but sure, we could put parentheses around those. Absolutely.
Why doesn't the plus c get a parentheses? Like, why is the plus c not included?
Well, you have an infinite number of integrals here. Each one, like you're adding up an infinite number of integrals. Every integral has its own little constant of integration. If you added up all the little constants of integration, you could just combine them all together into one big constant of integration, c.
I guess.
Okay.
Yeah, I guess that makes sense. Okay.
All right. Good question. Good question. Now, one thing I'll mention here, because we're basically at the end of our class. The final part of this, I mean, that we did good, everything's good, but remember how I told you we can take a expression like here's our power series representation for this integral, but maybe instead of starting at the index n equals 0, we want to start at the index n equals 1. If we do that, then because we are starting our index later, we have to subtract 1 from all the n's. We have to subtract 1 from all the n values. And then that allows us to rewrite our power series starting at n equals 1. This is helpful to be able to do because, again, sometimes in the homework, even on the exam perhaps, you might have a problem, where it's like multiple choice, select the right power series, and maybe the right one starts at index n equals 1. You don't want to force yourself to pick a wrong answer, right? Based on the index, you want to pick the right answer, and sometimes that means your nice answer, you might have to change the index to try to match one of the answers in the homework. And I'll mention too that in your homework for section 8.6, which is due on Monday, you have a few problems where you're going to be getting a power series, and you're going to be approximating, well, you're going to have an integral, a definite integral, and you want to approximate the power series, or the integral correct to within a certain level of accuracy. Well, the power series that you're going to see, like this one, are alternating power series. So you could use the alternating series estimation theorem to help you. And example 8 from section 8.6, example 8 is a very good example to help you see how to do that. You'll need to look at example 8 from section 8.6 in your ebook to help you with perhaps like the last couple questions from your homework. But it'll be fine. It'll be fine. You'll be fine. We've touched upon the key ideas in section 8.6. Well, and then example 8 will be another example that's good to look at. Are there any questions at all before I stop the recording here? Okay, I'll stop the recording. Thank